Inhibited growth and decay. Our objective is to solve differential equations involving inhibited growth and decay. Inhibited, remember, means restricted or hindered. So we have inhibited growth, which is where there is an upper value, call it m in this picture, that the amount y cannot exceed. Notice that it looks like it's growing exponentially, and then it kind of peters off and gets closer and closer to that amount. That differential equation looks like this. dy dt equals k times the difference between the larger value minus the smaller value. Y is the smaller value approaching that upper limit for k positive, and like I said, for y less than m. Inhibited decay is when there is a lower value m that the amount y cannot go below. Similar differential equation, dy dt equals k times the difference y minus m, this time y being greater than m, so y subtract m. So to point out some similarities, the differential equations look very similar. The rate of change of the amount is proportional to the difference between an amount and another amount. Notice the rate of change is proportional to two amounts. Well, in this one, inhibited decay, y is greater than m, so big minus small, and in this one, y is less than m, still big minus small, so that value multiplied to k will be a positive in either of those instances. Another similarity and difference, k is positive for uninhibited growth, and k is negative for uninhibited decay, similarly to uninhibited growth and decay. Let's take a look at an application of inhibited decay. Newton's law of cooling. Suppose an object is heated to a temperature, we'll call it y sub naught, for an initial amount. Then at time t equals 0, the object is put into a medium with a constant lower temperature, causing the object to cool. Newton's law of cooling states that the rate of change of the temperature of the object with respect to time is continuous and proportional to the difference between the temperature of the object, which we're calling y, and the ambient temperature, which we're calling m. You might think of m for medium. The ambient temperature means the surrounding temperature. Think of placing an object in a room. The room temperature would be the ambient temperature. The room would be the medium. The differential equation is like what we showed for inhibited decay. dy dt, the rate of change of the amount, equals k, that's the proportional to part, y minus m. Because the object is warmer than the ambient temperature, it comes first, y minus m. Let's take a look at solving this differential equation. We start by separating the variables, y and t. So if dy is over here, this part that has the y in it needs to go to the other side, so we divide both sides by y minus m. We end up with 1 over y minus m times dy equals, and we want the variable t to be on the other side, so we multiply both sides by dt. So that makes k times dt. Now that we've separated and have y's on this side and t's on this side, we're able to take the integral of both sides. Remember that m is a constant and k is a constant. Taking the antiderivative of 1 over y minus m, because y is to the first power, we get natural log of the absolute value of y minus m equals, and the antiderivative of k with respect to t is kt plus c. Now remember that we are using y greater than m. So in that case, this value will always be positive, and we can remove the absolute values. Natural log of y minus m equals kt plus c. Now we apply our initial condition, which is that the y value at time 0 is represented as y sub naught, similarly to when we did uninhibited growth and decay. So it looks like this to solve for c. Natural log of, instead of y sub naught minus the constant m equals k times 0 plus c. K times 0 is 0, so natural log of y sub naught minus m simply equals c. Now we plug that value of c back into our general solution here and rewrite that general solution as natural log of y minus m equals kt plus, and then the c value, natural log of y sub naught minus m. Now we have an acceptable general solution where we know the c, but we are going to simplify this because we can. Let's bring the natural logs to the same side by subtracting that natural log expression. So natural log of y minus m minus natural log of y sub naught minus m equals k times t. Remember that subtracting logarithms means we can condense it into one logarithm. So we can write this as natural log of y minus m divided by y sub naught minus m equals kt. I can get rid of the natural log by exponentiating both sides. Base e, both sides become the exponent to base e. That gets rid of the natural log, and we're left with y minus m over y sub naught minus m equals e to the kt. We're going to solve to get the y by itself, so we need to multiply by y sub naught minus m on both sides, and we get y minus m equals y sub naught minus m times e to the kt. One last step to get y by itself, adding m to both sides, which is y equals y sub naught minus m times e to the kt plus m. And there we have our solution, our general solution from our differential equation. It's very similar to the general solution of uninhibited growth and decay, where we have the initial value in front of e to the kt, but now because we have this temperature of the room, the surrounding medium, we've got the initial temperature minus that room temperature, and then at the end plus the room temperature. So there are ways to see similarities and make connections. Most importantly, it's important to remember that for Newton's law of cooling, or inhibited decay, we start with the differential equation dy dt equals k times y minus m, and end with the general solution y of t equals y sub naught minus m times e to the kt plus m. Let's take a look at an example that applies Newton's law of cooling. An object is heated to 90 degrees Celsius and allowed to cool in a room with a constant ambient temperature of 20 degrees Celsius. That 20 is our m. If after 10 minutes the temperature of the object is 60 degrees Celsius, what will its temperature be after 20 minutes? Let's start with the fact that we are experiencing something cooling. So that's using Newton's law of cooling, which starts with the differential equation. The rate of change of the temperature is proportional to the temperature of the object minus the surrounding medium temperature. This differential equation will always solve to y equals y sub naught minus m, the initial temperature minus the room temperature, times e to the kt plus m, the room temperature. Now we have some information that we can use to plug in here, like we know that m is 20, and we know that the object is heated to 90 degrees. That means our y sub naught is 90. So let's plug in those values. Y equals 90 minus 20 times e to the kt plus 20. Simplifying gives us y equals 70 times e to the kt plus 20. We're given a little bit more information about how, after 10 minutes, the temperature of the object is 60 degrees. So when T equals 10, the Y is 60. We can use that information to find the value of K to get a better particular solution. So we plug in 60 for Y and 10 for T. Solving to get K, we start by subtracting 20 from both sides and get 40 equals 70 e to the, I'm going to write that as 10K. Then we can divide both sides by 70, so 40 divided by 70 equals e to the 10K. And instead of 40/70ths, I can divide by 10 and get 4/7. I can take the natural log of both sides to get the K out of the exponent, and I'm left with the natural log of 4/7 equals 10K. To get K by itself, I need to divide by 10. So K equals the natural log of 4/7 divided by 10. Let's rewrite that particular solution, but with the K value in it. So now we have Y equals 70e. Instead of KT, we can write this as T times natural log of 4/7 divided by 10. Now you may be wondering why it seems like K is a positive value. But remember, when that number inside the natural log is less than 1, we can think of that as 7/4 to the -1 and then move the negative in the front. So another way to think of this value of K is the negative natural log of 7/4 divided by 10, and therefore another way to think of this is Y equals 70e to the -t times natural log of 7/4 divided by 10. Now it's a little bit more obvious that we're dealing with an inhibited decay equation. Let's use this equation to answer the question, what will the temperature be after 20 minutes? So when T equals 20, we will figure out what Y equals. Let's plug in 20 for T. Y equals 70e to the -20 times natural log of 7/4 divided by 10. And at this point, we go to our calculator. Well, I just realized I forgot the rest of that particular solution. Let's not leave that out. Let's go back to where we wrote that particular solution and put in the plus 20. And where we have the T value plugged in, put in the plus 20. Now we can go to our calculator, typing that in to get a value that makes a little bit more sense when we're trying to figure out a temperature. Typing that in, we get that temperature is approximately 42.857 degrees Celsius, since we're working all in degrees Celsius. So its temperature after 20 minutes is approximately 42.857 degrees Celsius. Thanks for watching.